Thank you very much for the opportunity to speak here. So I'm going to speak about some joint work with Marie-Claude, Arnaud, and Claude Viterbo. And so it will be mostly applications of this completion of the space of Lagrangian with the spectral norm, with respect to the spectral norm. And okay, and the main application I will present is this higher dimensional generalization of the Birkhoff attractor. Okay, and what we will use is not only the fact that gamma is well behaved with respect to symplectic maps, but also with respect to conformally symplectic maps. Okay, so let me start by introducing conformally symplectic maps. So before introducing them, let me so recall some sort of the classical terminology. So for simplicity, I will assume that we are on a cotangent bundle of a manifold M. Okay, and there we have coordinates Q in the base, and P in the fiber. And we have a canonical one form, which is the Liouville form. Lambda equals PDQ, and the standard symplectic form is minus d lambda. Okay. And if we take a Hamiltonian, so a Hamiltonian is just a function that depends on time. So this is the Hamiltonian. We can associate to it a vector field by the following. So we get a vector field x sub t, which is defined by omega of xh is dh. Sorry, it's xt that I wanted to have here. So it's a time-dependent vector field. Omega of xt is dht. Okay, so it's like a gradient, but with respect to the symplectic form instead of the Riemannian metric. Okay. Now so it's known that this generates an isotopy by T, which preserve the symplectic form. Okay. But and now I want to sort of introduce a friction term. So this is supposed to, classical mechanics, this is supposed to model systems with no dissipation of energy. And so if I introduce a friction term, which is parallel to velocity, then we need to consider an extra term here that I write in green, minus c lambda for some constancy. Okay. Eventually, c could depend on time, but that's okay like this. Okay, and the result when we do this change is that here we have an exponential minus ct appearing in the equation, and so that motivates the study, the dynamical study of conformally symplectic maps. So maps psi. So let me define. We take a diffeomorphism psi, and we say that it is conformally symplectic. And then I will write CS if phi, sorry, psi star omega is A times omega for some A. Okay. Of course, if A is 1, we are in the symplectic case. And now I will impose a slight another restriction. I will say that psi is conformally exact symplectic. So that I will write CES.
But A is a constant, not a function, right? A is a constant.
It's a constant, yes. So in fact, in dimension 2, it could be, so that there's a small lemma that says that if in dimension at least 4, you cannot have a function which is non-constant here. This cannot happen.
Okay.
So it's not a big restriction, but except in dimension 2. So it's a conformally exact symplectic if it behaves well with respect to the Liouville form also. So if we have something like this, plus some exact form. Okay. A priori, this is closed, and we say it's exact if the remainder we have here is exact. Okay, but in fact, it's not a big restriction because there's an observation by Marie-Claude, Arnaud, and Fejos that says that every CS map is conjugated by a symplectic map to a conformally exact symplectic map. Okay, so from now on, I will restrict to CES maps. And A is called the conformal ratio. Okay. So there's so I said the basic examples are the Hamiltonians with frictions, and there's maybe the most basic example is when the Hamiltonian is 0. So I'm not sure if it's represent a motion or something, but if H equals 0, then in that case, the vector field we get is radial in the fibers. So we get the standard Liouville vector field. Which is radial in all cotangent fibers, in all T star Q M. Okay, so we have the 0 section, and in each fiber we have everything converges to the 0 section. Okay. Okay, and so apparently it seems that from this type of dynamics has not been studied much by mathematicians so far, except in dimension 2. In the new page. Okay, so in dimension 2, so somehow let's say it's not studied much so far, except in dimension 2. And in dimension 2, that's where the classical Birkhoff attractor is defined. So now I will speak about the classical Birkhoff attractor. And this goes back from 1932, I think. Okay. So I will now explain the construction of Birkhoff. Okay. So in that case we have psi, which is a diffeomorphism from A to A. In fact, it could also be a homeomorphism, but let's say diffeomorphism for simplicity, where A is the annulus, so S1, the compact annulus, S1 cross -1, 1, and we can see it as being included in T star S1. Okay, so it's a compact part in T star S1. And we assume, so here in dimension 2, so we can assume that A is non-constant. Okay, so we assume psi is dissipative, which means that psi star omega, so the symplectic form, the area form, is A omega for some A, which goes from A to R, and such that A is between 0 and 1 strictly. Okay, so it really strictly contracts the area. Okay, and we also assume that say psi of the annulus is strictly included in the interior of the annulus. So it's included in S1 cross -1 open. Okay, so I can start to draw a picture. So this is S1. -1. So S1 is represented by a segment here. And so what my assumption is that the annulus is sent into something smaller here by psi. And now if I start to iterate psi, then this the annulus which was sent onto the between the two green curves is sent to an even smaller piece. I don't know, something like this maybe. Okay, at the second iteration we get something like this, and then to something even smaller. And in the limit we will see some possibly complicated sets that I will draw in red. So for example, you could have something like this, but you could also have some hair in the limit. Okay. So the red thing that I drew here, I will denote it by C0, and this is just the intersection of all psi n of the annulus when n when you take all n's, all integers, all positive integers n. Okay, so this is somehow that's a compact invariant compact subset. It's somehow the bigger invariant compact subset, and somehow to study dynamics, you would be interested in finding smaller invariant compact subsets. And what Birkhoff did is to somehow cut hair. So if you cut all the hair, then you get something which I drew in yellow in the picture. Okay. And this will be the Birkhoff attractor. So what does it mean? So we cut hair. What does it mean? It means that sorry, so we consider A minus the nth iterate of A, okay? This has two connected components, un plus and un minus, so two connected components. So for example, on my picture, u1 plus is here, u1 minus is here, and then u2 will be the u2 minus will be the bigger thing, and u2 plus will be this, and then we have a un plus and a un minus after iterations. And then if we set u plus to be the union of all un plus and u minus similarly, then u plus is everything which is above the red thing, and u minus is everything which is below the red thing. Okay, and now the Birkhoff attractor that I will denote C of psi is by definition the closure of u plus intersected with the closure of u minus. Okay, and this is the yellow part. And this is what is called the Birkhoff attractor. Any question? Okay, and so people has used this to study dynamics of dissipative twist maps. I cannot say more, but there have been works on that, and we can give some examples. So, for instance, if we consider a pendulum, you know that the phase space of the how you call it in English, I don't know, but when you represent the level sets of the Hamiltonian for the pendulum,
the phase portraits.
Phase portrait, okay, like in French, in fact, and then so you see something like this. Okay, so that's in the QP coordinates, and we know that the dynamics when there is no friction follows these curves. Okay, and now when you add this friction term, then you should have a Birkhoff attractor, and the Birkhoff attractor will look like spirals like this. I'm not sure if you will be able to understand, but the picture, but okay, so it's like an infinite spiral that converges to the center, and then there's a sort of symmetric spiral that exits. So that's the Birkhoff attractor in this case. Okay. Okay, and then it can also be very complicated. For example, in some cases, it's been proved that it is an indecomposable continuum. So that indecomposable continuum means it's a connected compact subset which cannot be written as a union of two connected compact subsets, which are non-trivial. And so, I mean, it's hard to imagine what it is. For example, a curve is not like that. So it can be, in general, it can be very complicated. But what is known is that it is an annular subset, and so known. So maybe fact that this set is connected, and the complement has two components. Exactly. Two connected components. Okay. Now let's come back to a general conformally symplectic map. So let psi be a CES map on a cotangent bundle. And so it's kind of clear that the construction we just seen is doesn't apply directly. For example, there's no we can consider C0 is well defined. So C0 was this set here, the intersection of all the psi end of this bundle. This is well defined, and you get something invariant. But then how do you cut hair? I mean, this procedure of considering the upper part and the lower part, and then taking closure doesn't work in higher dimension, because there's only one connected component in the complement, and so when you take closure, you will just get everything. So it's defined, but it is not clear how to define. Well, how to cut hair somehow. To cut hair. And so that's where we will use the completion, okay, and the gamma support. So idea is use gamma completion. Okay. So as in the talk of Claude, I will consider L0 to be the set of all closed exact Lagrangians. in the cotangent bundle. Sorry, and I know that on this space there is the spectral metric gamma. And in fact, this metric is well behaved with respect to conformally symplectic map. Proposition is that if I take L0, L1 to be two exact Lagrangians, and I take psi to be a CES map of ratio A, then gamma of psi of L0, psi of L1 is A times gamma of L0, L1. Okay. So in the symplectic case, we saw in the talk of Claude that this is true already. Huh? We said it's an isometry. Psi acts as an isometry in the symplectic case. Here, it's not an isometry, but it's Lipschitz. Psi acts in a Lipschitz way on the completion, on L naught. Okay, and so it extends to completion. And furthermore, if we assume that A is less than 1, then it's really a contraction that we have on this space. And so there will be a fixed point. Okay, and so maybe I should state what we get. So somehow for the first part, all you need to know is the Banach fixed point theorem. So if A is less than 1, then psi admits a unique fixed point that I will denote L infinity, and this leads into completion. I forgot the hat here. Extends to completion. Okay. So that's kind of obvious. And then as a consequence, if we consider the gamma support of L infinity, this is a closed invariant subset of T star m. Oh, sorry, of psi in T star m. Okay. So this thing I will denote B of psi. So again, this is easy once you know the existence of the gamma support, then this comes somehow for free. And what is perhaps less trivial is the fact that this coincides with the classical Birkhoff attractor in dimension 2. Moreover, if M is equal to S1, B of psi coincides with the Birkhoff attractor. C of psi that I just defined. Okay, so from the point of view of dynamical systems, it's interesting. I mean, we have a closed invariant subset, which is canonically associated to the map psi. And it generalizes something classical, so we can try to study it. So at this point, I mean, I can just repeat what Claude said. So for example, we know that B of psi is gamma coisotropic. That's one property. So this closed invariant set is kind of quite big. It's coisotropic. We know that it will intersect all exact Lagrangian submanifold. It also follows from what Claude said. We know something on the homology. We know it intersects all fibers of the cotangent bundle. So that's so we know some things. Okay. Okay.
Vincent, So
yes.
in the case where you're looking at, say, a Liouville manifold, so this generalizes the singular Lagrangian skeleton, right?
Yes and no. So if you're so you're in a one-chain case, for example, or this will be included in the skeleton, let's say. Okay, it will be included in the skeleton. Now, in the skeleton, you can have some isotropic parts that you will not see here because it has to be co-isotropic.
Okay.
And also, if you have a complicated manifold, the skeleton could have several, how to say, handles or something, and then maybe it will. Then you have several classes of exact Lagrangians, and for each class, probably you will have a different Birkhoff attractor. Okay, but we haven't studied this case much.
Okay, thanks.
But this result, of course, generalizes to any exact symplectic manifold. Okay, so I would like to give a few ideas about how we prove it coincides with the Birkhoff attractor. So ideas for why we have this equality. So I won't give the whole proof, but just some ideas. And there's an important key lemma somehow that it's a general fact about the gamma support is that if we have some LK smooth Lagrangians which gamma converge to some L which belongs to the completions, then the gamma support of L is included in the lim inf of the LK as subsets. So I think the lim inf can also be written as the set of all limit of xk when we take points in the LK. Okay. And this is kind of obvious from the definition of the gamma support. So but somehow it's useful to know. And now also a consequence of it. So let me consider. So I'm in the annulus now. So and I want to consider the Lagrangian lambda, which is S1 cross B in the annulus. Okay, so this is just a straight horizontal line at height B. This is the zero section. And now if B equals 0, then it's easy because lambda is exact. It's the zero section, okay? And so we know that by the fixed point theorem, right, that psi k of lambda converges to L infinity, the gamma metric. And so we deduce that, so at this point I don't deduce anything, but we have this fact at least when B equals 0, okay? And now if B is not 0, then it's not exact, but I can still consider psi k of lambda. And it's not exact, but I can sort of make it exact by some translation. So I do some translation, and I have to translate by a minus a to the k b. That's a horizontal translation. Okay, in that case, we can show that this thing, which is exact, will converge to infinity for gamma. Okay. And now, if I take B to be included in U1 plus, sorry. So U1 plus, so remember there was the annulus like this. And after my first iteration, the annulus was sent to something smaller. So U1 plus, U1 minus. And I assume that B is included in U1 plus. This exists. And in that case, then I know that, then I know that B of psi, so is by definition, it's the gamma support of an infinity. And using the lemma above, we know it's included in the limit of this tau minus AK B psi K lambda, which is exactly the same thing as the limit of psi K of lambda. Okay. And this thing is included in the psi K of U1 plus, which is what was psi K should be here, which is what I denoted UK plus earlier. Okay. So I proved that B of psi is included in, there's a union, there's a missing union here. Okay, this is included in the union for all K and the union for all K, and then I need a closure here for this to be true. Okay, the limit is included in the closure of all this. Okay. And this thing is exactly what I denoted U plus bar like this. And so we have B of psi, which is included in U plus closure. And for the same reason, it will be also included in U minus closure, which is by definition C of psi. Okay. So somehow using this this lemma above and some tricks, we can easily show that you have this inclusion. And now the reverse inclusion is kind of even easier. I mean, this C of psi has a minimality property, which is well known. It's minimal among all compact connected subsets which are invariant and separates the annulus in two components. Okay, and so as a consequence, we get the equality quite easily. Okay. I don't know if there is any question about all this before I move to something else. I would like to present a second application, which is maybe more like a motivation to studying completions. So that will be a weak version of the nearby Lagrangian conjecture. Which I will write NLC. Okay. So what is this conjecture? So that's a conjecture which I think goes back to Arnaud, which says that every exact Lagrangian submanifold in T star M is Hamiltonian isotopic. So there's a, yes, it's Hamiltonian isotopic to the zero section. Okay. So it's really a central conjecture nowadays. A lot of people has been working on that, and but it's still open. Except in the, so it's true. It's true in some cases. It holds on T star S1. That's not too difficult. It's known to be true also on T star S2, and I realized that I forgot to check the attribution of this fact. I don't know, maybe someone knows in the audience. Okay, and then there's also, it's also true, it's also known to be true on T star T2. And I also forgot the names of all the authors, except that I know that there is a Dimitroglu Ritzel among them. Ritzel. I think there's Ivry as well. And I forgot. I think here there are also several authors, but I forgot. But I mean, that's the only cases which are known. Okay. And in more general manifolds, there's a theorem by Abu Zaid and Krag that says that every exact Lagrangian is homotopy equivalent to the base. I mean, the projection onto the base induces a homotopy equivalence. Okay, so in general, we are quite far from having it. On the other hand, it's already a very strong result. It was a lot of technology involved to prove this. Okay, and somehow what we have a kind of easy proof to a weaker result. Okay, so that's the thing we call weak nearby Lagrangian conjecture, is the fact that for any exact Lagrangian, smooth. Oops, what happened? Uh-oh. Okay, my software crashed, but it should. Okay, sorry. Can you see my screen or?
I can see it, yes.
Yes,
okay.
We can still read.
Okay, except that you cannot see anymore what I wrote, but that's okay. I'm going to rewrite the theorem.
Yeah.
Sorry. There's a problem. It's now my tablet who. No, it's the software again. Ah. Give me. It's for the suspense. Again. Okay, it's going to work. Sorry. Maybe not. Yes. Okay, so let me write my theorem. Apologize. So we take 8 for any L in L0, so an exact Lagrangian submanifold. Is the image of the zero section by an element not in D ham, but in its completion. with respect to the spectral norm. Okay, so this thing is the completion. With respect to the metric gamma that we saw. Okay. So I don't know if it's how interesting it is, but somehow it gives you some tool to study exact Lagrangian, for which we don't know how Hamiltonian isotopic to identity. For example, if you know some invariants are well behaved under these completions, then you can use this maybe. And also perhaps it's a motivation to study further these completions. Okay. I think I have something like 20 minutes, so I think I have time to give you some ideas for the proof. Okay. So we know that the zero section is fixed by the Liouville flow of lambda, right? By the Liouville of lambda, which is PDQ. Remember, this Liouville flow was this radial flow that was converging to the zero section. Okay, and in fact, it's more general. There's a fact that every maybe I should say any closed Lagrangian, exact Lagrangian is fixed by some Liouville flow. So the meaning is that if you change the Liouville form, it's possible to find a Liouville form such that the associated Liouville flow will fix the given Lagrangian. Okay, and it is possible to build something like this for any Lagrangian by some elementary methods. And furthermore, we can, moreover, we can assume that this new Liouville flow will differ from the previous Liouville flow just by a Hamiltonian map. Assume that, so if I denote by psi1 this new Liouville flow, time one map of this Liouville flow, this will correspond. This will be this can be written as psi0 composed with h. So psi0 will be the time one map of the standard Liouville flow. Psi1 will be the time one map of the new Liouville flow of, so maybe I should call it L of the Liouville flow associated to L. And so we can assume that these two differ by a compactly supported map. So this thing is in D ham C of T star M. Okay, so that's some elementary construction that we can do. Now there's a lemma. Is that psi1 and psi naught are conjugated. Not in conjugated by an element in in DHAM, but not in DHAM, in the completion of DHAM. Why is this lemma true? We just consider T, the map that goes from DHAM to itself, and which takes an element U and associate to it psi 0 inverse U psi 1, which can also be written psi 0 inverse U psi 0 H. Okay. And in fact, there's a property of gamma that tells you that this is a contraction. Okay, so gamma is a contraction, T is a contraction. And so since we are in this complete space, we have a fixed point. So this follows from the properties of gamma. For example, the fact that it is B-invariant, the fact that it is well behaved with respect to conjugation by conformal maps. And so there's a unique fixed point. I will denote U infinity. And you see that what we get from the fact that it's a fixed point is that psi naught is U infinity psi 1 U infinity inverse. So that proves the lemma. Okay, and now so remember what I wanted to do is show that any Lagrangian, exact Lagrangian, is the image of the zero section by an element in the completion. But you see that if psi 1, so it's not if, it's since we know that psi 1 preserves L, then obviously psi 0 will preserve the image of L under U infinity. But now it's psi 0 is the standard Liouville flow, so the only thing which is preserved is the zero section. So we necessarily have U infinity of L is equal to the zero section. And that's how we prove this nearby Lagrangian, this weak version of the nearby Lagrangian conjecture. So all you need to know is Banach fixed point theorem plus a few elementary constructions. Okay. I don't know if there is any question about that. So now, since I still have a few minutes, I would like to use them to maybe sketch the construction of gamma, since perhaps after all this, maybe you would be interested in seeing that. So a sketch of construction of the metric gamma. So this is kind of completely independent to the rest. Okay, so we take L0 and L1 to be two Lagrangians in exact Lagrangians in the cotangent bundle, let's say. And then since they are exact, by definition, this means that the Liouville form restricted to Li is exact. So we can write it as dfi for some fi. Okay. And if I take an intersection point x in L0 intersect L1, then I can consider the action of x, which will be f1 of x minus f0x. Okay, so this is the action, by definition, this is the action of the intersection point. Okay, of course it depends on the choice of fi, but okay. So maybe one example is if L is the zero, L0 is the zero section, and L1 is a graph, so the graph of the differential of function. Then in that case, I can take, for instance, f naught to be 0 and f1 to be f. Maybe f pulled back by the natural projection. And then in that case, the action is just the value of x. And saying that x is an intersection point means that x is a critical point of f. Okay, so in the case of graph, this action is just this. The new page. Okay. Now there's something called the Floer complex. Which is abstractly defined as a vector space. It's just formally generated by the intersection points. Okay, and there are some subvector spaces, so I can add a subscript T here. Okay, and this will be the subspace which is generated by points x with action less than t. I can consider these subspaces. Okay, and this is, so it's a big theorem by Floer that this thing carries a differential. Which is constructed by considering moduli space of geolomorphic curves, and it's a long story. And so from that we get groups HFT of L0 and L1, which are the Floer homology groups. Okay. Okay, and so in fact it's been computed. If you consider the whole vector space, so when t equals infinity, when you get all intersection points, then it's isomorphic to h star of m, to the cohomology of the base, the manifold. And this is a theorem by Fukaya, Seidel, and Smith. But before that, Floer proved the case where L1 is Hamiltonian isotopic to L0. Okay, Floer proved it when L1 is isotopic, is Hamiltonian isotopic to L0. Okay. And now from this homology, you can define what's called spectral invariance. You take a homology class in M. Okay, so you can see it by the Fukaya-Seidel-Smith theorem, you can see it as a Floer homology class as well. And you look at, and you define the number L alpha, L0, L1 to be the infimum of over all T, all real numbers T, such that alpha is represented in the subcomplex. So it's represented by in the sub at the level T. Okay. You know that when T is infinity, that it will be represented because of the Foucault-Saddle-Smith theorem. So there's a minimal level at which it's represented. Okay. And we can even explain this by a picture. So on some examples. So for example, if you consider the case where L0 is the zero section and L1 is the graph of the F, then in that case, these homology groups are isomorphic to the sublevel, to the homology of the sublevel sets of the function. Okay. And so in that case, this L alpha L0 L1 is really like the lower level at which the homology class is represented. So I can draw a picture. So if I consider if I see F, for example, as a function of torus like this, and if I take alpha to be a class represented by a meridian on the torus, then we see that the lowest level under which the class is represented is exactly this one. Okay, that's the lowest sublevel set under which in which the class alpha is represented. Okay, so in that case, the number L0 L1 is exactly this critical value of F here. Okay, and now I can just need one line to tell you what gamma is. Gamma is just so that the definition that I mean, these numbers were already defined by Claude and extended using to Floer homology by Schwarz and O. So gamma is by definition the gamma of L, not L1, is by definition L when you apply to the fundamental class of M minus the same thing but to the point class in M. And 0 and 1. Okay, so that's how this metric gamma is defined. So it's quite abstract because I mean you need to know Floer theory and all that. But on the other hand, it's I mean we have a lot of structure on Floer theory, so all these structures can be used to give inequalities on the gamma metric. For example, to prove the triangle inequality, you need to know the product structures. And somehow all this rich structure of the Floer homology can be used to study this gamma. And I think I will stop here. So thank you very much for your attention.